Hello everyone. So this is tutorial 3 in the course Drone Systems and Control, where we cover extended Kalman filters. In the previous lecture you have gone through Kalman filtering techniques, which is a very useful mathematical tool for state estimations of linear systems. Now in tutorial 3 we will see how estimation becomes difficult by Kalman filter in nonlinear systems, and in that way we need to understand how estimation can be done for nonlinear dynamical models. We will see how to derive Jacobians for extended Kalman filter. Then we will learn EKF's prediction and update steps as it was there for Kalman filter also. Then we will apply EKF for a drone example for state estimation, and we will discuss about strengths and weaknesses of extended Kalman filter in the context of estimation for drone systems. So, what is EKF? What is extended Kalman filter? Kalman filter assumes linear models and Gaussian noise. In real world systems, the dynamics or sensor models are often nonlinear, which is very practical, and that is how we consider systems in our regular practical life. Then EKF is an extended version of Kalman filter which handles nonlinear systems via linearization. What is the meaning of linearization? How we linearize? That I will come in later slides. So, what are the applications of extended Kalman filter in drones? EKF is used in sensor fusion for estimation. It is used for estimating position, velocity and orientation from IMU and GPS. It is used for visual odometry, external disturbances and estimation. When there are wind gust in the drone systems, then estimating the wind gust as external disturbance can be done by extended Kalman filter. And for drones specifically, estimating the attitude and altitude is also can be done by extended Kalman filter, which is very useful. So, what I will say here is that extended Kalman filter has lots of applications in drone systems, drone control, and with that we will try to understand more about EKF. So, it is one extended version of linear Kalman filter, as I have already told. How it is extended? It is extended in such a way that it can handle nonlinear dynamic system models, right. So, what is the basic idea? When Kalman filter is used, Kalman filter directly handles the linear dynamical systems. When that system has some nonlinearity, Kalman filter performance degrades. Now, what extended Kalman filter does is that it linearizes the model, approximates the nonlinear model using the first order Taylor series expansion. When we do that, that item or that particular mathematical term is called Jacobians. So, the linearization is done by Jacobians, then the linearized models are used to apply standard Kalman filter equations. Okay. So, most of the steps or in the EKF algorithm resembles with Kalman filter algorithm as well, but there are certain differences. When it is a nonlinear model, then first you have to linearize it by Jacobians. We do it by first order Taylor series expansion, and then we get the model, we use it in the algorithm. Extended Kalman filter is used when system is approximately linear in small neighborhoods around the current estimate. So, if the linearity is not moderate, then sometimes we can face some problem with extended Kalman filter as well, but it works well for systems with moderate linearity, nonlinearities and Gaussian noise. Fine. Okay. Now, we will just go through a few recaps of linear Kalman filter. What we are doing in Kalman filter is that we were taking the linear model, which was in the form of x dot equal to Ax plus Bu and z equal to Hx. So, this was the state equation. This is the state equation for a linear system. The first equation is state equation, where the second one gives measurement. Okay. Now, for discrete Kalman filter, we discretize this system in this form. Then we were having process noise and measurement noise, and this was the entire system representation which was dealt by Kalman filter. Kalman filter assumes linear models and it assumes Gaussian process noise and measurement noise. So, these terms represent process noise, this term represents measurement noise. What are the steps? The major steps in Kalman filter algorithm was predicting the next state and covariance, and then updating using the measurement vector and the innovation, updating the next state and covariance. So, these were the two steps which will be summarized in the next slide. So, this is the discretized linear system as we have seen. This is the measurement equation. These parameters are noise parameters. So, x k is the state vector. As an example, it can be position or velocity of the drone. U k is the control input, which is the acceleration, and z k is the measurement vector, which is actually the sensor data, what we are getting from the sensor. Now, what is process noise? Process noise here is represented as W k, which is a Gaussian noise with 0 mean and a covariance q. Similarly, measurement noise or sensor noise is represented as V k, which is another Gaussian noise with 0 mean and covariance r. So, what is q? Q is the process noise covariance, r is the measurement noise covariance. Fine. So, what is process noise? You have seen in the last lecture that a process noise is the uncertainty in system dynamics which happens because of model mismatch, unknown external forces and system noise or approximation errors. Okay. But measurement noise on the other hand is due to the uncertainty in the sensor measurements, sensor limitations, quantization error, electronic noise, environmental interferences. These are the source of measurement noise. So, when these things are there in the system, Kalman filter can handle these in spite of having all these noise components in the state models. Kalman filter can handle the state estimation or parameter estimation of linear systems. What it does is that first it predicts the state and covariance, then it updates, and iteratively it goes on repeating the steps for some particular time. At each time step, Kalman filter performs two main operations to estimate the system state. The first one is the prediction or time update. So, what is done here is that you use the system model to predict the next state and the uncertainty. It comes here. Then estimates the next state before the new measurement arrives. So, with the previous measurement only, it estimates or predicts the state at this particular stage. After that, what it does is that it predicts the covariance. Okay. So, and process noise covariance matrix is involved here. So, Q is a matrix, R is also a matrix, and this denotes process noise. Okay. So, it projects the previous state forward in time. From k minus 1 we predict for k using the system dynamics. What is the system dynamics here? It is x dot equal to a x plus b u. When it is discretized, then it becomes x k equal to a k x minus 1 b k b u k minus 1. X k dot in discretized system becomes a x k minus 1 plus b u k minus 1, and then it predicts the covariance. After that, the innovation vector is calculated, which involves the measurement and the matrix H, which is the output matrix. Innovation y k is the bridge between prediction and the update. Then innovation covariance is also calculated. After that, the major step is computing the Kalman filter gain. So, once we have the Kalman filter gain, we go for updating the estimate and the covariance. So, in the next step, after having the Kalman filter gain computed, the estimate state estimate is updated. So, we get x k in terms of x k given k minus 1, which we got in the first stage here. Now, it updates the state estimate, then it updates the covariance, and it goes iteratively like this. So, when we get this x k and p k, we use it for the time step k plus 1. Okay. So, what is done in the measurement correction or update step? It is done as it corrects the predicted state using new measurement information. Okay. So, what are that? This is the new measurement information at kth time step, at time step k. Fine. It reduces uncertainty by balancing the model and sensor reliability. So, in the prediction step, Q was involved, in the correction step R was involved, and with that it finds a balance between the model error and sensor error and reduces the uncertainty. So, for further reading, you can go through the book Optimal State Estimation, Kalman Filter, H Infinity and Nonlinear Approaches by Dan Simon. Good. Okay. So, what are the key components of extended Kalman filter then? Now, we understand that EKF is one extended version of Kalman filter to handle nonlinearity. We know what were the steps in Kalman filter algorithm. Now, we will see that what are the new additions of steps in extended Kalman filter algorithm. So, what we have now is the state equation, which is nonlinear. It is given as x dot equal to f x comma u. That means x dot is a function of both the state and the control input vector. So, x is the state as it was shown in the previous slides and u is the control input. Okay. Now, we have the nonlinear measurement function, which is denoted as a function h. Previously, what it was? It was x dot equal to a x plus b u. We, for the case of linear systems, we could write it in the forms of matrix and vector, but now when it becomes a nonlinear system, we can't do the same thing. Then x dot becomes a function, nonlinear function of x and u. Now, for extended Kalman filter, the added step is this linearization, where Jacobian is computed by Taylor series expansion. So, Jacobian of f, that is the function f, is computed by this, taking the derivative at this step. Then Jacobian of h is computed, and these two we use as matrix in the next state. Okay. Process and measurement noise covariances are already there in the consideration, which was there in Kalman filter as well. So, the importance of good modeling and tuning cannot be ignored in terms of Q and R, which was the similar case for Kalman filter as well. Okay. Now, extended Kalman filter does the same thing. It predicts the state and the covariance at time step k. So, this is the state prediction and covariance prediction at time step k given the measurement at time step k minus 1, and it is done like this. We have this function and we have the Jacobian. From function f we have got f k, fine. So, this Jacobian is used here and we get the prediction on covariance, fine. Now, what is done is computing the Kalman filter gain, which is already there in computation of Kalman filter gain for Kalman filter algorithm as well. In the same way we do it for extended Kalman filter. and after that there is a correction step. What we do is that now we estimate x k in terms of the measurement at step k. Okay. And after that this is the innovation, and after that we estimate p k, that is the covariance at time step k. So, this is the workflow of extended Kalman filter algorithm. We can see that it uses the same prediction step and correction step. The steps also look similar, but there is one hidden thing which happens inside is that we have to compute the Jacobian matrix. Now, what Jacobian is doing is that in terms of getting the Jacobian, we linearize the system, then a standard Kalman filter also can be used. So, you can see that what algorithm we are doing is also the having the similar steps as Kalman filter algorithm. So, once we get the Jacobian and linearize the system, we can use the Kalman filter gain and then estimate the state and covariance at time step k. So, this is the extended Kalman filter flow diagram. First we have to initialize the system or algorithm with the initial state and covariance. With that we predict the state and covariance for the next time instant. Once we get these two, then we go for Kalman filter gain. So, once that step is also done, then we have the Kalman filter gain, we use it to estimate finally the state, and this is the state and the covariance at time step k, at k, fine. So, in this way extended Kalman filter algorithm iteratively works and then it gives the estimate. We will go through an example and then it will be more clear that how extended Kalman filter works better than Kalman filter when the process is a nonlinear process or the system is a nonlinear system. In general, we run the Kalman filter or extended Kalman filter once per new sensor measurement. So, the number of iterations, how many times this algorithm will run is dictated by the data availability, sampling rate and the kind of application we are doing, the duration of those applications. Okay. We can also do event based triggering where the algorithm is updated or the state and measurements covariance are updated when any motion is detected by the vehicles. Fine. Okay. Now we have one example of drone yaw control. You have seen this example in Kalman filter lecture also. What we have here is that we have a state x k which is the yaw angle psi k. So, this is the yaw angle. Then we have a control input u k which is the yaw rate. Fine. So, yaw rate command is the control input and yaw angle at time step k is the state. Okay. Now, the yaw dynamics looks like this, psi dot is equal to omega and then we have the process noise. Fine. Nonlinear measurement is z, which is sine of this angle yaw angle, and then we have measurement noise. So, when we are talking about the state we have process noise, when we are talking about the measurement we have the measurement noise, and then Kalman filter assumes a linear measurement. When we solve this particular system with Kalman filter, then it assumes a linear measurement directly without having a Jacobian. How it can be done? It takes sine psi equal to psi by small angle approximation, fine. But EKF uses a true nonlinear measurement, it takes Jacobian, it plots now when the Jacobian is obtained, then we can say that it is linearized in a different way. So, this small angle approximation does not give accurate information about the system, but Jacobian has more accuracy regarding this. Then we show here the plots of estimation and estimation error. So, when we estimate the yaw angle, we get it like this. You can see the black line which is the true yaw angle, The blue one is the Kalman filter estimate. You can see that though the black line is going like this in this fashion, the blue line, which is the Kalman filter estimate, is not being able to track that. But with Jacobian, calculating Jacobian and having more nonlinear information into the system, extended Kalman filter estimates much better than the Kalman filter. So, when we plot the error, estimation error, we can see that Kalman filter and extended Kalman filter are kind of working in the similar way here in the initial time steps, but as the time is higher, we see that Kalman filter performs poorly due to its linear measurement assumption. It is taking directly sin psi equal to psi, fine, but EKF will track the true EO more accurately. That is why you can see that the error, mean of the error is almost 0, which is not there for Kalman filter. It has huge error. This particular example shows that when it is a nonlinear model, extended Kalman filter handles the nonlinearity in a better way, which Kalman filter cannot do, and that is evident in the simulation results. Okay. Now, what is important for designing a proper extended Kalman filter based estimator is tuning it properly, because we know that process noise Q and measurement noise R play a very important role in estimation performance. So, EKF performance depends heavily on choosing appropriate noise covariances, process noise Q, which denotes model uncertainty, measurement noise R, which denotes sensor accuracy. Okay. Now, if there is a poor tuning of Q and R, then we can see that there will be some slow convergence. That means the error will be high for a long time, and then after that it might reduce. Then there can be some underestimated uncertainty, and filter divergence also can happen if the Q and R matrices are not properly tuned. Fine. Like Kalman filter, extended Kalman filter is also a trade off between trust in model versus trust in sensor. When it is a high Q and low R, then we can tell that the sensor is working better, so we rely more on measurements. When it is a low Q and high R, we will say that the model predictions are better. Okay. So, with these considerations and having cross validation and domain knowledge, what application domain we are talking about, we can strike a right balance between Q and R, so that it gives a balanced performance and a better estimation. Fine. So, what are the limitations of extended Kalman filter? We have seen that Kalman filter fails to accurately estimate the model or accurately estimate the states and parameters when it is a nonlinear model. Why? Because in the example you have seen that sin psi was taken as psi by small angle approximation, but when extended Kalman filter calculates the Jacobian, it has more information within it about the nonlinearity of the system. But the problem is that EKF works well for certain systems where nonlinearity is moderate. So, first order approximation by Taylor series approximation can give rise to some large errors when the nonlinearity is strong. You can go through some examples in the reading materials, which will show that extended Kalman filter always does not work very well in giving state and parameter estimation. Okay. What is the problem? If the nonlinearity is very strong, then the Jacobian can be complex and it can be hard to derive. So, if the Jacobian is not having accurate information about the nonlinearity, then the EKF may diverge because of poor linearization. Okay. There can be inconsistencies, covariance can become too much optimistic. If we do not have right balance between Q and R, then also there is a problem. Another important aspect of extended Kalman filter is that it handles Gaussian noise well, as it was for Kalman filter. But when it is a multimodal, Gaussian noise is one unimodal distribution like this, but when we have a multimodal distribution something of this sort, then extended Kalman filter does not work well. So, These are some of the limitations of extended Kalman filter, and now the immediate question which comes to our mind is that whether there are any alternatives. Yes, there are some alternatives. Extended Kalman filter is based on first order linearization using Jacobians, works well for mild or moderate nonlinearities. That means when the system is highly nonlinear, it can't work. It might be difficult to derive the Jacobian, and non-Gaussian noise or multimodal distribution also is a problem for EKF. To balance all these limitations of extended Kalman filter and also handling nonlinear system, there are some other variants called unscinded Kalman filter, where Jacobians are not calculated. What we calculate is called the sigma points. There is particle filter which can work well for non-Gaussian or multimodal distribution. There is another variant called factor graph SLAM, which is like useful because of its nonlinear optimization based approach. However, as we told, EKF can handle moderate nonlinearity in a better way, and compared to these variants, EKF works better when computational efficiency is critical. What does that mean? EKF computes the Jacobian, which can be difficult for strong nonlinearity, but for moderate nonlinearity, calculating Jacobian is not a computational burden for the system. So, it can be done with a better computational efficiency. But when we take unscinded Kalman filter or particle filter, though they higher accuracy in estimation, but the complexity also rises, which is a problem in real time implementation. So, complexity also rises like this. Fine. Now, if you want to know more about unscinded Kalman filter, particle filter or factor graph based SLAM methods, then I suggest you going through this particular reading material. So, to summarize, what we learnt here in tutorial 3 is that extended Kalman filter extends Kalman filter to nonlinear systems using linearization. How is it linearizing? By calculating the Jacobian. Fine. This Jacobian is a local linearization. So, it is near the point of estimation and checking the neighboring points and linearizing it. Effective for many real world estimation problems, specifically when it comes to drone, then EKF has lots of uses. And then it requires careful modeling and tuning. If we do not have Q and R properly tuned, then sometimes it can diverge. So, modeling or tuning is a parameter of high consideration. Now, there is a trade off which extended Kalman filter provides, that is simplicity and approximation errors. What is that? When we use extended Kalman filter, though it is more complex compared to Kalman filter, that is the linear version, but what happens is that compared to the nonlinear filters or nonlinear estimators, extended Kalman filter implementation is quite simpler. However, we have seen that when strong nonlinearity comes into picture, then there will be some estimation errors, and that can be handled by some other variants of filters like unscinded Kalman filters, particle filters, etc. So, since for simple nonlinearity it works well, it is widely used for autonomous systems. Fine. So, for further reading, I would suggest you to go through this book Estimation and Tracking by Bar Shalom, Lee and Kirubarajan. Then Optimal State Estimation, Kalman H infinity and Nonlinear Approaches by Dan Simon, which is a very elaborate derivation of Kalman filter and extended Kalman filter both in continuous and discrete time domain. You can go through Probabilistic Robotics by Thronberger and Fox to read the other variants of filters which give better performance compared to extended Kalman filter in terms of or in the presence of strong nonlinearity. And there are some MATLAB examples which are very useful in this particular link, which you can follow and then write your own code. Thank you.